Okay, our next speaker is Marta Redovsky from Simvestab in Mexico City, and she will tell us about genus fields of Kummer extensions of rational function fields. Please go ahead.
Thank you. Thank you for the invitation and thank you for the organization, Florian and Tom. This is the organization of the talk and the abstract. We obtained the genus field of a general Kummer extension of a global rational function field. And first we study the case of a Kummer extension of degree a power of a prime. Then we prove that the genus field of the composite of two abelian extension is equal to the composite of the genus fields of the extensions, but under the condition that the degrees of the extension are relatively prime. That's a sufficient condition. And as a consequence, we obtain the genus field of a general Kummer extension. So that's the program. As the origins, we have the work of Gauss, where he introduced the concept of genus in the context of quadratic equations. And Kummer was interested in a genus theory for Kummer extensions, where by the time the Kummer extension was an extension of this type. K is equal to the rational numbers with this primitive root of unity, and the K is the original little k with a radical of this type. L is an odd prime number. Now we consider a Kummer extension is a finite Galois extension, k over k, and for some given integer n larger than 1, we have k contains the nth roots of unity, k over k has a abelian Galois group G of exponent n. That's a Kummer extension. In this case, we have G1 up to GH, the various CELO subgroups. Then G is equal to the direct product of the CELO subgroups. And these subgroups have order a power of a prime. In this case, we have that K is the composite of the corresponding fields. Now, the context we are in is a global rational function field, little k equal to fq of t, and fq is a finite field with q elements. Rt is the ring of integers, a ring of polynomials, and Rt plus is the set of monic irreducible elements of Rt. For a polynomial n, this k of lambda n denotes the n cyclotomic function field, and this lambda n is the nth torsion of the Carlitz module. For convenience, we will call a field f a cyclotomic function field if it's contained in one of these. That's to for economy. Well, at this moment, I emphasize that there's this parallelism between number fields and function fields. So the corresponding to this k is the rational function, the rational numbers. This Rt corresponds to the integers, and this would consist of the prime numbers, the positive prime numbers. And this is the classic cyclotomic field. Here we will introduce this notation for a polynomial d. This star is this expression. The corresponding one in number fields is for a prime p, or not prime p. It is -1 to the pi minus 1 over 2 times p. And we consider the infinite prime in our context. is the pole of the divisor T. And well, this infinite prime is corresponds to a non-Archimedean valuation, and the case for number fields is the absolute value, the regular absolute value that corresponds to an Archimedean valuation. So there are similitude and differences. So this is a difference. And we denote K of lambda n plus the maximal real subfield of K of lambda n. And for a field that is contained in K of lambda n, F plus is the intersection of these two. Given a finite extension, K over K, we define the Hilbert class field KH of K as the maximal unramified extension of K, such that every element of the set S of divisors of K dividing P infinity decompose fully in KH over K. This is what we will consider as the Hilbert class field. And the genus field Kg of K is, with respect to the little k, the field below, is equal to the composite of the original K and K star, where K star is the maximal abelian extension of K contained in KH. In the particular case that K over K is abelian, that is, we are in this case, Kg can be considered as the maximal abelian extension K containing K, such that Kg over K is unramified and each element of S decomposes fully in Kg over K. So we are not referring to KH at this moment. Let F be a cyclic atomic function field that is contained in the K of lambda n. The genus field Fg is M plus F, where M is the maximal cyclotomic extension of F unramified at the finite primes. And we denote it this way, and we know it by the name of the extended genus field of F, or narrow genus field. And then, of course, Fg is equal to the plus extended genus field of F and composed with F. Let me comment here that going back to Gauss, but in the modern language, we have that for a quadratic field, quadratic field, the 2 rank of the extended class number is the number of primes dividing the discriminant minus 1. That's for the extended class number. If we want to consider the class number, then this is the number of primes that I mentioned. Sometimes it's minus 1 and sometimes it's minus 2. Therefore, this extended or narrow situation is more benevolent, at least in some cases. Well, this extended genus field is the field associated to this Dirichlet character or group of characters, where X is the set of Dirichlet characters associated to F. So in the case of F, this could be mixed up, and then with Y we separate them. And that corresponds to this extended genus field. We obtain that this extension is totally ramified at every element of S, and this degree is equal to these ramification indices. Therefore, to obtain Fg, we need to compute a subextension of degree of this type. Let L be a prime number. This preliminary result says that if we have a cyclic Kummer cyclotomic function field, so it's inside cyclotomic K of lambda n, and it's just one prime L, and it's just one radical, the polynomial is like that, then the extended genus field is this composite. And now let me introduce more notation. So we go to a more general case. So we have a Kummer cyclotomic L extension, but now it's the composite of this. So we have still one L, prime L, but we have several radicals. And then we introduce all this notation. And well, this field is contained in a cyclotomic one. We consider the primes that ramify. We consider the ramification for the finite primes and for the infinite prime. Consider also these numbers. And then we obtain a nice expression for the general, for the extended genus field. It's like that. We introduce more notation, NM, and also NI that we can choose or obtain. And in this case that we have a Kummer cyclotomic L extension of K with all the conditions as above, one prime L and several radicals, we have two cases. If M is equal to T, the M and T defined before, we have that the genus field is equal to the extended genus field. It's this nice expression. But if M is larger than T, then we have to consider all these things, and our genus field is the composite of all these that get quite complicated, as you can see. Now we get to this more general situation where we don't require that we are in the cyclotomic field. We might be out, but it's still a Kummer extension. Still, we have one prime L and several radicals. The things we do now is we obtain a field, an auxiliary field E that is contained in a cyclotomic one. And then in this case, the genus field is this composite or this composite, that is the same, where we have all these E's, and then we have an U and epsilon J. These EIs or EJs that we have here corresponds to E in the place of K. So in practice, it could get very complicated, but still explicit. And now I give an example that is an elaborated example of Carlos Daniel Reyes. He's still considering only one prime L and only one radical, but the Q is a prime, is this prime, large prime, and he's considering several polynomials. He's not giving them explicitly, but we know they exist. And these things, some are given and some others are calculated. We have the M that we were talking about is equal to 5, I think, because I cannot see it now. And T is equal to 2. And then the I that I was mentioning before happens to be 3 in this case, and the E3, this EI, is this one. The others are like this. And then finally, the genus field of the original field is this complicated expression. So you can imagine that it gets very complicated when we are in more general settings, but still it's explicit. Now, we are dealing with only one prime L. We want to have several primes. Therefore, we have to consider the composite of two fields. And we would like that the genus of L is equal to the composite of the genus of L1 and L2, but it's not the case. We have a contention, but generally we don't have equality. And in this example, we present the proper contention. So L1 is this K of lambda PQ, and L2 is K of lambda RS. Well, actually plus the maximal subfields. So they are here, sorry. Then it happens that we can calculate that the genus field of this one is itself, the gene of this one is itself, and so the composite of the genus fields is L, but L, that is the composite of L1 and L2, the genus field is this one. So it's a proper contention, the degree is Q minus 1, that's important that Q is larger than 2. So we have this proper contention in this case, so, but still we want to see on the, we want a sufficient condition for it. So we have several steps, previous results that I'm showing you the way that we did it. We have that a prime divides the degree of L over K if and only if it divides the degree of LG over K. That's the first one. Another one is that if we have a cyclotomic extension, L divides the degree of L over K if and only if it divides the degree of the extended genus field over K. And if we have two cyclotomic fields and the greatest common divisor is 1, then we have this with the maximal real subfields. We have also that if the degrees are relatively primes and they are both cyclotomic, then we have the equality we want. And finally, in this one, we remove the condition that it's contained in a cyclotomic field. And it's just that the degree of the extensions are relatively prime, and in that case, we have the equality. And therefore, we obtained our main result that we have a Kummer extension, not necessarily a cyclotomic, of order n, that is the product of these primes, powers of primes. Then K is the composite of these auxiliary fields. Then we have that the genus field is equal to the composite of all these. And now this could be very cumbersome, but still explicit. They are computed in theorems 2 and 3. Well, let me tell you about the references. In this reference are developed several things, but also these Dirichlet characters for function fields. In this one, that is with the colleague, we work with genus fields of cyclic L extensions. This is a previous result of Hu and Lee that talks about genus fields of Artin-Schreier extensions that are what unrelated to us at this moment. And Leopold, who developed this technique of Dirichlet characters for number fields. These two are our very original papers with this colleague. And there we were getting not explicit expressions. This is the pioneering work of Peng. That is the first one we know. It's genus fields of Kummer function fields. He considers extensions of the degree L, just that. So we have been generalizing all these things. This is the paper of Reyes Morales and Villa Salvador, my co-author, where they developed this example. This is the paper that we have by now in arXiv, where we have the proofs and arguments for this talk. And these are two extra references. So that's it. Thank you very much.
Thank you, Marta, for your talk. Are there any questions?